After studying this chapter, you should be able to do the following. Name and describe the two atomic mechanisms of diffusion. Distinguish between steady state and non-steady state diffusion. Write Fick's first and Fick's second law in equation form to solve steady state and non-steady state diffusion respectively. Note the kind of diffusion for which each of these equations, meaning the Fick's first equation and Fick's second equation, is normally applied. For the non-steady state diffusion, we should be able to write the solution to Fick's second law for diffusion into a semi-infinite solid when the concentration of diffusing species at the surface is held constant. So based on that condition, we can write a solution to the Fick's second law. And again, you should be able to define all the parameters in this equation. Calculate the diffusion coefficient for a material at a specified temperature given the appropriate diffusion constants. Many reactions and processes that are important in the treatment of materials rely on the transfer of mass, either within a specific solid or from a liquid, a gas, or another solid phase. And this is necessarily accomplished by diffusion. Diffusion is defined as the material transport by atomic motion. And this can be the net flux of any species, including ions, atoms, electrons, holes, etc. And the magnitude of diffusion depends on the concentration gradient and temperature, which we'll discuss later. Materials of all types are often heat-treated to improve their properties. The phenomena that occur during a heat treatment almost always involve atomic diffusion. So among the hundreds of engineering applications of diffusion, let's take a look at a couple of examples. First example is the cauterization for steel surface hardening. And this is a steel gear that has been case hardened. That is, the outer surface layer was selectively hardened by a high temperature heat treatment during which carbon from the surrounding atmosphere diffused into the surface only. It's not all the way into the core, but it's only to a surface layer. And the case appears as the dark outer rim of that segment of the gear that has been sectioned. And the increase in the carbon content raises the surface hardness, which we'll learn later, and which is in turn leads to an improvement of the wear resistance of the gear. The occurrence of diffusion may not always be beneficial. In some applications, we may want to limit the occurrence of diffusion for certain species. For example, the diffusion of carbon dioxide in plastic soda bottles must be minimized. And this is one of the major reasons why we use polyethylene terephthalate or PET to make bottles that ensure the carbonated beverages they contain will not lose their phase for a reasonable period of time. So again, diffusion is defined as the material transport by atomic motion. So diffusion can occur in all phases, including in liquid phase, in gas, and in solid. So in this class, we'll focus on diffusion in solids. But just to comparison and to give you some kind of background knowledge, let's review mechanics of atomic motion in gas and liquids as well. So in gas and liquids, we all have this kind of experience, right? When you drop a drop of the ink or food dye into water, it will just spread all over the water after a period of time. So this is caused by the random motion of atoms, or is termed as Brownian motion. Same idea for gas. Well, if you spray some perfume at one corner of the room. After some time, you will smell the perfume all over the room. So this is also Brownian motion of atoms. So that's the mechanism of diffusion in gas and liquids. In solids, which we are going to learn in a second, the mechanism of diffusion is vacancy diffusion or interstitial diffusion. The phenomena of diffusion may be demonstrated with the use of a diffusion couple, which is formed by joining bars of two different metals together so that there is intimate contact between the two faces. So here in this example, we have a couple of copper and nickel. And we have the schematic representations of atomic positions and the concentration profiles. So from the atomic position, we see from on the left, or for the copper bar, we only have copper atoms at the beginning, and for the nickel bar, we only have nickel atoms at the beginning. For the concentration as well, across the copper bar, the concentration of copper is 100%, the concentration of nickel is 0. While on the nickel side, the concentration of nickel is 100%, and there is none copper inside the nickel. And then this couple is heated for an extended period of time at an elevated temperature. And this temperature is below both the melting point of copper and nickel. So after a period of time, we're going to cool this couple down to room temperature. And this is what we get after the chemical analysis. Again, we have the atom position schematic of the atom position and the plot of concentration versus position. So we can see that the pure copper and pure nickel at the two extremities of the couple, but it's separated by an alloyed region. So within this region, we have both copper atoms and nickel atoms, which can also be seen from this concentration position profile. At the far left, we have 100% copper, but the concentration of copper is decreasing to the right or into the nickel side and decreasing all the way to 0. For the nickel as well, at the far right, the concentration is 100%, but it's slowly decreasing, not sharply into 0, but gradually to 0, all the way to the copper side. So this result indicates that copper atoms have migrated or diffused into the nickel, and that nickel has diffused into copper. So this process by which atoms of one metal diffuse into another sometimes is termed as interdiffusion or impurity diffusion. Let me write that down. Interdiffusion or impurity diffusion. So on the other hand, there can also be self-diffusion. If there's only one type of atom in pure copper, for example, there's also diffusion. There can also be diffusion happen, which is called self-diffusion. So for no matter what kind of diffusion in this, there is a net drift or transport of atoms from high to low concentration regions. So the driven force is the concentration slope. It's always driving from high concentration region to the low concentration region. We just mentioned self-diffusion. Self-diffusion happens in an element solid where there's no second type of atoms, only one type of atom. For example, in pure copper again. So in element solid or in any solid, the atoms are not just staying at their position forever is not just staying there, but atoms jump around from one lattice position to another, and this is called self-diffusion. Self-diffusion can be detected using radioactive tracers, where we can label some atoms, and after a period of time, when we check those labeled atoms, they are no longer at their original spot, but they kind of moved to other positions. Well, this generally does not significantly affect material behavior, but we should know atoms do move their spot around from lattice position to another. Well, there's one thing that I should mention is I missed something from this lattice position or lattice arrangement, which is vacancies. So think about if there's no vacancy, the atoms has no spot to move. There's no way for the atoms to move. So I should have included some vacancies. For example, here is one vacancy or an empty spot, right? Where atom A can move into, or atom C can move into, or other atoms can move into. There should be another or other vacancies here. So eventually the atoms have empty spot to jump into, so they can jump around. So one thing that makes diffusion possible is the presence of those vacancies. And vacancies are also moving around because they're kind of exchanging positions with atoms. Interdiffusion refers to the diffusion happens in an alloy where you have different types of atoms. So atoms tend to migrate from regions of high concentration to regions of low concentration. Again, the concentration slope is the driving force for diffusion. For example, in the copper-nickel example, at the beginning, copper has 100% concentration at the left region, while 0 concentration at the nickel region. After a short period of time into diffusion, we can see copper atoms start to migrate to the lower concentration region, where is the nickel region. And eventually, copper atoms will be randomly distributed throughout the nickel, where the concentration for the copper is constant throughout the copper-nickel couple. And we have a copper-nickel alloy. So at this point, there is no difference between the concentrations, or there's no concentration slope, or we can say the slope is 0. So the diffusion stops. One mechanism involves the interchange of an atom from a normal lattice position to an adjacent vacancy, or weakened lattice site, as shown here, is termed as vacancy diffusion. So which can be illustrated on an increasing elapsed time scale. So where, and again, this atom jump or exchange positions with the adjacent vacancy. As a result, we can see the vacancy becomes here because the original atom left its spot, which will leave a vacancy. Looks like they exchange the positions. Okay, so this keep happening. This another atom jump to this adjacent vacancy site, which will leave its original position as the vacancy, and so far so on. Because diffusing atoms and vacancies exchange positions, and the diffusion of atoms in one direction corresponds to the motion of vacancies in the opposite direction. And both substitutional impurity atoms and self-diffusion occur by this mechanism, vacancy diffusion. And the rate of vacancy diffusion depends on the number of vacancies, the more vacancies we have, the more vacancies in the material, the quicker the vacancy diffusion will be. And also the activation energy to exchange. And this energy depends on the temperature. The higher the temperature, the higher the activation energy is. The second type of diffusion involves atoms that migrate from one interstitial position to a neighboring one that is empty, meaning a neighboring interstitial site. So here is a demonstration of the interstitial diffusion. Small interstitial atoms move from one interstitial site to an adjacent interstitial site. So typically, interstitial diffusion occurs much more rapidly than diffusion by the vacancy mode because, one, the interstitial atoms are more smaller than the vacancies or than the atoms, and thus more mobile. And two, there are more interstitial positions than vacancies present in the material. Thus, the probability of interstitial atomic movement is greater than for vacancy diffusion. Often, it is necessary to know how fast diffusion occurs or the rate of mass transfer. And this rate is frequently expressed as a diffusion flux. But first, let's take a look at what is a flux. Flux is not only used for diffusion, but you may also hear mass flux, heat flux. So in general, a flux is a flow per unit area per unit time. And in this class, the diffusion flux rises from experimental measurement, and it is defined as the mass or equivalently the number of atoms or moles diffusing through and perpendicular to a unit cross-sectional area of solid per unit time. So in mathematical form, this may be expressed as mass over cross-sectional area over time. And the unit can be moles per cubic centimeter per square centimeter second, or kilogram per square meter second, or atoms per square meter second, depends on the given units and the specific problem. Well, generally, whenever a flux is multiplied by an area, a rate is obtained. So the rate is, for example, mass per unit time is the rate. And whenever a flux is multiplied by both area and time, an amount is obtained. In this case, when we multiply the flux by area and time, we can get the mass or the moles or the number of atoms. Fick's laws of diffusion arises from the experimental observation that mass flows from high to low concentration. And Fick's first law of diffusion solves steady-state diffusion. It states that diffusion flux is proportional to the concentration gradient dc over dx. In math expression, J equals to negative d times dc over dx, where J is the diffusion flux in the units of mass per unit area per unit time. D is the diffusion coefficient with the unit of square meters per second. And C is the concentration of diffused species. The unit will be mass per cubic volume per volume, mass per volume. And the negative sign indicates the diffusion direction is opposite to that of the concentration gradient. In other words, it diffuses from high to low concentration. Fixed first law is applied to steady-state diffusion. Steady-state means the diffusion flux is independent of time. So it's time independence. And let's take a look at one example to apply the fixed first law to the diffusion of atoms of gas through a thin metal plate, where the concentrations or the pressures of gas on both surfaces of the plates are held at constant. PA and PB, those pressures or concentrations do not change over the time or at any times. And this diffusion process eventually reaches a stage wherein the diffusion flux does not change with time, which means the mass of diffusing species entering the plate on the high pressure side, PA is higher than PB, by the way, equals to the mass exiting from the low pressure surface. So there's no net accumulation of diffusion species in the plate. And again, this is the example of steady-state diffusion. And the concentration profile, which is the concentration of the diffusing species, we use the letter C. This concentration plot with the position X, it's a linear relation, and it always like this. This profile doesn't change with time. So as one example, if we choose one location, for example, in the middle of this plate, at time 1, for example, after steady state of diffusion has been reached at 0 second, if the concentration, let's call that, is CO, for example, if we're taking a look at the concentration at this place, here is XA and XB and X0. At t equal to 0 second, C0 is here. And after, for example, 100 or 1,000 seconds, when we take a look or measure the concentration again, the C at this location, C0 is still C0, and CA is still CA, CB is still CB. So the concentration at any location is a constant, is independent of time. So this is what's called steady-state diffusion. And also, for steady-state diffusion, the diffusion or the concentration profile, which is plotted in figure B, is assumed to be linear. You can see that's a straight line. So if that's linear, the concentration gradient is linear, then we can write this equation. The concentration slope or the concentration gradient dc over dx is approximately delta c over delta x. And again, because it's linear, well, if we use the two end spots to calculate the slope, we have CB, or let's look at 2 points. On this point, the x-axis is XA and the y-axis is CA. And at point B, the x-axis is XB and the concentration is CB. So the slope can be calculated using the two locations or the 2 points at both ends, where we have CA minus CA, CB minus CA over XB over XA, and that's the concentration gradient for steady-state diffusion, which is a linear concentration profile. How do we tell this is the steady-state diffusion then? Well, based on the given concentration profile, if the diffusion flux is constant, J is constant, the concentrations on both sides are held constant. In this case, CA and CB are constant. And the concentration gradient is constant, or in other words, the concentration profile is linear. then we say this is a steady state diffusion, and we can apply the fixed first law to solve or figure out any concentration at a given location. Let's take a look at one example. Methylene chloride is a common ingredient of paint removers. Besides being an irritant, it also may be absorbed through skin. When using this paint remover, protective gloves should be worn. If butyl rubber gloves, the thickness is 0.04 centimeter, are used, what is the diffusive flux, which means diffusing flux or diffusion flux of methylene chloride through the glove? And the data given are the diffusion coefficient in butyl rubber, D is 110 times 10 to the negative 8th cubic or square centimeter per second. So diffusion coefficient is given, and surface concentrations both outside the glove and inside the glove are given, where C1 is higher outside glove, which is 0.44 gram per cubic centimeter, and inner, which is close to your skin, C2 is 0.02 gram per cubic centimeter. And we're looking for the diffusion flux, J, when D and C1, C2 are given. To solve this problem, first we're going to assume this is a steady state diffusion problem. So we're going to assume it's already reached at an equilibrium state or steady state, so the concentration gradient doesn't change with time anymore. The concentrations at both surfaces are held at constant values. So C1 and C2 are constant, and the thickness or the difference between the locations, the positions, is the thickness of the glove. Here, this surface is outside the glove, and then here is inside the glove, contacting with the skin, and outside the glove is contacting with the paint remover. So if we assume this is a linear concentration gradient or is a steady state diffusion, then we can use Fick's first law, where J, the diffusion flux, equals to negative D, diffusion coefficient, times the concentration gradient. And since it's a linear concentration gradient, so we can use C2 minus C1 over X2 minus X1. Again, X2 minus X1 is the thickness of the gloves, and C2 and C1 are the concentrations at both surfaces. Here are the given information. The diffusion coefficient D, C1, C2, and X2 minus X1, which is the thickness of the glove. We just need to substitute those data into the Fick's first law. You need to convert certain, there's no need to convert units as well, right? All the distance are given in terms of centimeter, and the time is in second. The math is in gram, so J is solved to be positive 1.16 times 10 to the negative 5 gram per square centimeter per second. And that's again why we have a negative sign in the Fick's first law. And your answer should be a positive value.